Welcome back to Robotic Mechatronics System Design course. We will continue with the rest of the lecture second, Sensors Used in MPS 500 Part 2. So in the previous part, we discussed different types of sensors used in the MPS 500. We watched lots of videos and we went through optoelectric sensors. Um, And we will continue in this lecture with different types of sensors, and we'll go deep into them and see how do they work and what are the main definition around these type of sensors. The first one is proximity sensor. Includes all sensors that performs non-contact detection. Proximity sensors convert information on the movement or presence of an object into an electrical signal. There are three types of detection systems that do this conversion. Systems that use the eddy currents that are generated in metallic sensing object by electromagnetic induction. Systems that detect changes in electrical capacity when approaching the sensing object, and systems that use magnets and reed switches. We will see each of these sensors and we will discuss in the coming slides how do they work. There are some useful YouTube videos that are handpicked, and you could watch them around the proximity sensor topics, but there are numerous videos on YouTube and on internet that you could watch by yourself and learn more about proximity sensors. So what are features of proximity sensors? Proximity sensors detect an object without touching it, and they therefore do not cause abrasion or damage to the object. No contacts are used for output, so the sensor has a longer service life, excluding sensors that use magnets. Unlike optical detection methods, proximity sensors are usable for use in locations where water or oil is used. Proximity sensors provide high-speed response compared with switches that require physical contact. Proximity sensors can be used in a wide temperature range. Proximity sensors are not affected by colors. Unlike switches, which rely on physical contact, proximity sensors are affected by ambient temperature, surrounding objects, and other sensors. Okay, so the first type of proximity sensors are inductive proximity sensors, which could detect magnetic loss due to eddy currents that are generated on a conductive surface by an external magnetic field. An AC magnetic field is generated on the detection coil, and changes in the impedance due to the eddy currents generated on a magnetic object are detected. So here we have a sensor and here we have a sensing object, and you see we have a transformer-like coupling condition between the sensor and the sensing object. So the transformer-like coupling condition is replaced by impedance changes due to the eddy current losses. So once we have an object, we have that induced eddy current in the sensor, and the sensor could detect the object. The next type of proximity sensors are capacitive proximity sensors, which could detect changes in the capacitance between the sensing object and the sensor. The amount of capacitance varies depending on the size and distance of the sensing object. So we have a sensor and the sensing object, and by changing the distance between the sensing object and sensor, we are changing the capacitance of the sensor. And that could be measured by the electrical circuit in the sensor, plus the capacitance of the sensor will change based on the material type of the object, and so the distance and the material of the object will change the capacitance of the sensor, and that could be detected by the electrical circuit of the sensor. So these type of sensors are not sensitive to the type of the material. They could detect either metallic or non-metallic objects. The next type of proximity sensors are read contact types. The read end of the switch is operated by a magnet. When the read switch is turned on, the sensor is turned on. So you could see the real read switch here, and what we have inside, we have two contacts, and there is a gap between these two contacts. Okay, and when we have a magnetic field, those contacts will be attracted by the magnetic field, and the switch will be on. So we will have a connection between the contacts or these reed blades, and we could have a electrical circuit. So here you could see a schematic of these type of sensors. You have a magnet and two reed blades. Once the magnet is close enough to the switch, then those reed blades will come together, and we will have a full connection of the blades, and the electrical circuit will be closed. Okay, so we have a table that compares different type of proximity sensors by their properties. We have an inductive proximity sensor on this column, and the second one we have a capacitive proximity sensor, and on this one we have a magnetic or read contact proximity sensors. On this column, or on rows, basically we have properties. We have a sensing object, we have electrical noises, power supply, current consumption, and sensing distance, ambient environment, physical vibration, shock, and assembly. Lots of information inside. I will go through the most important ones. For example, the sensing object, inductive proximity sensors could only detect metallic objects, iron, aluminum, brass, copper, etc. And capacitive proximity sensors could detect a metallic object, resins, liquids, powders, and etc. So basically, most of material, any metallic and non-metallic, and magnetic proximity sensors could only detect magnetic objects. Electrical noises could affect both inductive and capacitive proximity sensors because they work on a basis of electrical circuit, but they don't have, or almost don't have, any effect on the magnetic proximity sensors. Power supply, they work both on AC and DC. Current consumption varies based on two-wire models or three-wire models. Sensing distance also depends on the type and sensitivity of these type of sensors. Physical vibration shock could also basically affect any of them. And the assembly, they have sensitivity to the assembly and the material surrounding them, depending on the type. Okay, so let's go through a couple of explanation of terms for proximity sensors. We have a standard sensing object, which sensing object that serves as a reference for measuring basic performance. So this is a standard sensing object defined by the standard and by the manufacturer, is used to check the sensitivity for basically measuring this sensing distance or set distance or hysteresis and other properties. The sensing distance, as it is clear from the name, this is the distance from the sensing surface that the sensor could detect the object. Or which object? The standard sensing object, not any object. And if we go further from a sensing distance, then the sensor goes from on to off. Set distance, the distance from the reference surface that allows stable use. So you see that this is basically the vertical distance, and once we are in the set distance, we have a stable use and sensor could reliably and persistently could find the sensing object. Hysteresis, differential travel, the difference between the distance at which the sensor operates and at which the sensor resets. So if we travel frequently from a sensing distance to outside of the sensing distance, the sensor goes from on to off. And since they work based on capacitance or based on the eddy current, we will have a hysteresis effect inside the sensor, and it could basically affect the sensing or static sensing distance. The next one is response time, the number of detection repetitions that can be output per second. So for example, we have a sensing object that travels into the sensing area and off the sensing area, and by this action we will generate a pulse. The output of the sensor will be on and then it will be off. So if we move very fast, the response time of the sensor might not be enough to detect that movement. Response frequency, number of detection repetitions of output per second. So let's say we have a gear, or we have a queue of objects passing by, and sensor is going to detect those objects. If those objects travel very fast, sensor might not be able to detect those objects and could miss some of them between. We have two types of proximity sensors. We have a shielded and unshielded one. The unshielded one, as you could see, the sensor tip is free, so it doesn't have any shield. And you see the magnetic flux is spread in front of the sensor. But in the shielded one, the magnetic flux is concentrated in front of the sensor. So we could say that we have kind of like a polar beam or sharper beam that could detect objects with more accuracy, but the range of detection will be limited then. So how could we shield them? By mounting some metallic objects around the tips of the sensor. And we have two types of sensing distance. We have perpendicular sensing distance. if the sensing object moves perpendicular to the main axis of the sensor, or we have a horizontal sensing distance if the sensing object moves horizontally in front of the sensing surface. The perpendicular sensing distance expressed as the measured distance from the reference surface when the standard sensing object approaches from the radial direction. And the horizontal sensing distance expressed as the measured distance from the reference axis when the standard sensing object is moved parallel to the reference surface. The output configuration of sensors varies. We could have normally open, normally closed, and switchable normally open and normally closed contact switches. Normally open switches when there is an object in the sensing area, the output switch element is turned on. And normally closed when there is no object in the sensing area, the output switch element is turned on. So normally closed when we don't have any object, the output is true, the output of the sensor, and the sensor is on. And switchable, we could decide what is the normal condition of the switch. We could switch from the normally open to the normally closed. The output of the switch could be either NPN or PNP transistor output, or non-polarity or non-contact output. A general use transistor can be directly connected to a programmable controller or counter on NPN if the type of the PLC input module is also NPN. PNP transistor output primarily built into machine exported to Europe and other overseas destinations. But even for those PNP ones, the input module of the PLC should accept these PNP outputs. And non-polarity and non-contact output, a two-wire AC output that can be used for both AC and DC sensors, eliminates the need to be concerned about reversing the polarity. Okay, so this topic might be confusing for you now. Okay, just get yourself familiar with these terminologies. More detailed discussion will be covered in I/O interface topic or input-output interface topics. Microswitches. So far we discussed optoelectrical switches and the proximity switches. But what about mechanical contact switches? We call them microswitches. These switches are used as electrical limit switches. However, it should be noted that the switch point can be exceeded by only 0.5 millimeter. So how do they operate? Usually we need to have a contact between a part and a switch or a push button or a roller on these limit switches. We usually mount them at the beginning and end of actuators. For example, pneumatic actuators might have these limit switches at the beginning and end of their strike course. So they could have a normally closed contact or normally open contact and changeover contact. So they could have also different types. The changeover contact, we could decide what is the normal condition, what is the normal condition at the beginning. So if the switch is not in contact with any object and the output is on, so it is on the normally closed, let's say, state, and vice versa, it's on a normally open state. Another type of sensors that we have on MPS 500, but also could be found on a variety of uh, assembly lines and industrial operations and automation systems, are displacement encoders. They are basically a potentiometer, which they could measure the distance. So the type we have on the MPS 500 is a TRS 50S, a linear potentiometer for installing on cylinders using a mounting kit. If you refer to videos of MPS 500, you could find it on the testing station, where at the top of the elevator, the thickness of the object could be measured by these type of, or it could be checked at least. Okay, so it could be checked by these type of sensors. Okay, so how do they operate and work? Consists of a conductive plastic potentiometer, which is fitted in an aluminum housing. Okay, so this is a potentiometer in an aluminum housing. The sensing probe is of a stainless steel and supported in plain bearing bushes at each end of the housing. Electrical connection takes place via a 5-pin plug. Okay, it is a 5-pin plug, and you could change the let's say configuration of the sensor. The sensor is fitted by means of 4 retaining claws fitted into the grooves of the sensor housing. Okay, so it's all about how to mount those sensors. But anyway, is nothing more than a potentiometer, and you could see that we have, let's say, 24 or 48 voltage connected to the pin 1 and 3, and once basically the beam travels, okay, in and out, then the voltage between 1 and 2 changes, and this is the voltage that we want to measure, and we want to send it to the comparator or directly to the PLC if we have analog input module cards. The sensor serves as a height measuring device in the MPS system. Height measures from 0 to 25 millimeter at the voltage of 0 to 100% are converted. Why 0 to 25 millimeter? Because this is a stroke, basically length of this piston. This piston travels 25 millimeter, and so the voltage between the pin 2 and 1 changes from 0 to 100% of the voltage between the pin 1 and 3. So let's say we have 24 volt at 25 millimeter, we have 24 volt, at the 0 we have 0. Okay, so these are just characteristics of the sensor. I'm not gonna read them, just for your information. And since in the MPS 500 we don't have, or I could say on the testing station, we don't have analog input module on PLCs, then we need to have an analog comparator, because the output of the potentiometer is an analog signal, and that cannot be accepted by a PLC. So we need to have this. I will explain that. We have 2 knobs here, these 2 knobs, and we could, the operator could change the level of them. We have level 1 and level 2. Those basically changes the level of the voltage. And here we have explanation for each of these components on the comparator. One is the digital output. 2 is the display of the output error. So these are LEDs we have potentiometer level 2, this knob, the analog input for the reference voltage linear displacement sensor, 5, display of external operating voltage, 6 is the LED, 7 external operating voltage, 7 is here, 8 is a potentiometer level 1, the second basically knob here, and the 9 display of switching status of the output. So that 9 shows us what are exactly output of the comparator to the PLC, either on or off, because the output of the operator, comparator, is a digital output, either 0 or 1, false or true, and the input module of PLC accepts the digital input. So these 3 lights will show us the status of the comparator. I will explain the next slide on the graph. So the comparator converts the analog output signal of the linear displacement sensor in a digital output signal. 3 digital outputs are available. So not at the same time, of course we cannot have 3 digital outputs at the same time, but we could have any of these status. Okay, so it could be in the first one, measure value lower than the threshold 1. So level 1 and level 2, you remember that we had 2 knobs. Those are adjustable by 2 knobs by the operator, could be changed, and those levels are level of voltage. So at the max, let's say we have a 10 volt. Okay, so the voltage supply is 10 volt on this example, and if the voltage is less than level 1, then we have a low output. What is low output? This is something that we could define. It could be either 0 or 1. And then between level 1 and level 2, we have the mid one. Again, we could define the status of the mid. What is exactly mid? Once we fall between level 1 and level 2, what should we expect from the output of the comparator? Should it be 1 or 0? And then we have high once the level of voltage is more than level 2. So you could see here, for example, we could accept, so from the practical point of view, for example, we could only accept those objects or cylinders on MPS 500 if their thickness falls between level 1 and level 2. So remember that those voltages are analogous to distance. Okay, so level 1 means specific thickness, level 2 thickness, yes, and 10 voltage also a thickness or a full thickness or the whole course of that traveling piston of the sensor. So if the thickness of the object falls between level 1 and level 2, let's say we could adjust the comparator to give us output 0. Okay, and if the thickness of the thickness of the object is less than level 1 or more than level 2, it means that it's not a normal object, is off from the standard, and that should be rejected. So we could adjust that comparator to have output 1 on this case and on this case. So for both cases, the sensor output will be true. You will go to the PLC, and PLC program will understand if something is wrong, that object should be detected, and we'll go to another sequences of the program to reject that object. So we have the technical data for this comparator, again the operating voltage and so on and so forth, and that you could study by yourself. You see that, for example, what is the output of this switch is PNP, and we expect to have a PNP digital card or digital input module card on PLC. Okay, something that I believe is left behind on optoelectric sensors, and I would like to cover is more detail on retroreflective optoelectric sensors. So to understand the property or characteristic of retroreflective, we need to understand polarization of light. This is one property of light. Light can be represented as a wave that oscillates horizontally and vertically. So this is unpolarized light. The output of one LED, a normal LED, is unpolarized light. The light emitted from LEDs oscillates in the vertical and horizontal directions and is referred to as unpolarized light. Light from an LED that passes through a polarizing filter oscillates in only one direction and is referred to as a polarized light. So let's say we have a LED and then we have a polarizing filter here. That light, if passes from that filter, will be polarized. So let's say this one is a vertical filter, so the output will be a vertically polarized light. So that vertically polarized light cannot pass from a horizontally polarizing filter. Okay, it could only passes through a vertically polarizing filter. Okay, so now that we understand this concept, we will go to the MSR function. So MSR is a mirror surface rejection, is a function of retroreflective photoelectric sensors to receive only the light reflected from the retroreflector. By using the characteristics of the polarizing filter built into the sensor and the characteristics of the retroreflector. Okay, so here we have an emitter and we have a receiver, and here we have a retroreflector. Light that passes through a polarizing filter at the light emission side becomes horizontal. So this is an emitter. We have a filter that polarize the light horizontally, so the output will be horizontally polarized light. Light will change from horizontal to vertical if it is reflected on the triangular pyramid on the retroreflector. So we have this triangular pyramid on the retroreflector. As we said, that these retroreflector have specific properties. Yes, they are not a normal or simple mirrors. So now the light, you see, it was horizontal, now is vertical. And we have a vertical filter on the receiver. It only accepts those lights which are vertically polarized. So why we should use this MSR function? So if we use a normal mirror, or if we don't use these type of filters at the emitter and receiver, then the light could be reflected by any shiny object and those objects cannot be detected. Light will change from horizontal to vertical if it is reflected on the triangular pyramid under its reflector. The vertical reflected light passes through the polarizing filter at the light receiving side and reaches the light receiving elements. Using a sensor with MSR is ideal for detecting mirrors or other mirror-like objects. By using the principle described in the previous slide, a sensor with MSR can detect a mirror-like object as shown in the following figure. Note, if MSR is not used, the light reflected on the mirror-like object will be received, which will make it impossible to detect the object. The light will not be polarized at the object, and so the polarizing filter at the light receiving side will prevent the reflected light from being received horizontally. This makes it possible to detect a mirror-like object. So again, we have it. For example, we have this glossy object or can that could reflect the light, but since it cannot change the polarity of the light from vertical to horizontal or vice versa, then the receiver cannot detect the receiving light because the light won't pass through the filter.